Hello.
Yes, we
Yes,
can hear
sir.
you.
Good morning, sir.
Okay. All right. Can you see my screen?
Yes, sir.
Okay. Um, we'll start in 2 minutes just to allow for those who are signing in to sign in. Okay.
All
Yes,
right.
sir.
Okay. All right. I hope you cannot hear me.
Yes.
All right. We are going to start with our discussions on algorithms and data structures. And today's session is going to focus mainly on the introduction to our course, trying to understand where this course is coming from and what we are trying to achieve with it. So let's get into the introduction. Now, as I mentioned in our last meeting, this course is a programming course, right? It's a continuation of your programming courses. And I believe up to this point, you've done a course in structured program design. Am I correct?
Yes, sir.
Yes, please.
Yes. And you've done another course in programming with C++, right?
Yes, sir.
All right. So this course is a continuation of these programs. As I mentioned last time, those two courses are a prerequisite. That is, they are required to be able to take this course successfully. Now, at the heart of this course is a word we'll be hearing a lot, and that word is efficiency. Efficiency. So in the two previous courses that you've taken, you've learned how to write programs, basic applications, and so on. Now, in this course, we are going to continue the discussion on programming, but we are going to get a bit more advanced, right? We're going to learn to write a bit more advanced programs and run it, but not just write advanced programs for writing's sake. We must learn how to write these advanced programs more efficiently. So, if you take any computer program, right? If you take any computer program that we write, we are trying to do one thing, and that is we want to go from having a problem to having what? A solution. So, for instance, let's say I have an array of 100 values. I want to find the total, right? So, my problem is how to add up those 100 values so that I get the total as my solution. So, we want to go from having a problem to having a solution. Now, to do this, there are a few things that we need to do. One of the first things is we need to get the data, what we call the inputs, right? So if I'm adding up 100 elements in an array, those 100 values are my input. Now, when it comes to that input, the key thing that we need to worry about is how that input is organized. How the input is organized will have a huge impact on how efficient our program will be. Now, let me give a scenario. Let's say you've been given a task, and that task is to locate a particular page in a book, right? A book of 1,000 pages. Let's use that as an example. But when you come to find the page, all the pages in the book are scattered randomly in a room. Now, because the pages are randomly scattered in a room, it can be very difficult to find the page you're looking for. You might have to go through the entire room just hoping that one of the pages you pick up is the page you are looking for, right? However, if I take that same book of 1,000 pages and I organize them from page 1 to 1,000, and I say find page, let's say 350, right? 350. The task becomes much easier. I'm not saying it is easy, but it is much, much easier compared to when the pages are disorganized and spread randomly in a room. And so, what we are saying here is that when things are organized, it is easier to work with. And in this course, when it comes to inputs, data that we have to process, we are saying that we need a way to organize them efficiently. Because when they are organized efficiently, they are easier to assess and work with. And that is why we need data structures. We need the data structures to help us organize our data in a more efficient manner so that it is easier to work with when we are writing our programs. I hope I'm making sense of so far.
Yes, please.
Okay. So we need data structures to help us organize our data. That is why the first part of this course is looking at data structures. Now, once we've organized our data, to process the data, we need our algorithms, right? We need our algorithms to help us process the data that we have. So in this case, we say we are processing data. We have 100 values. We want to find the total, right? We need an algorithm to help us process. Now, when it comes to algorithms, if I gave every one of us today the same problem, we would write slightly different solutions to that problem, right? Now, let me give a scenario. So let's say I gave everybody in the class today a problem to go from here to Tamale, right? Your problem is to get from Accra to Tamale. Now, the way some of you will solve that problem will be to go to a bus station and board a bus. Some of you might drive there. Some of you might take your motorbike. Maybe some of you might even, because you don't have money, might walk there. Some of you might go to the airport and what? Fly to Tamale. At the end of the day, everybody will get to Tamale one way or the other. But it is not enough to say I got from Accra to Tamale. We need to then ask ourselves who got to Tamale in the most efficient manner. And by efficiency, we can, for instance, say who got there the fastest, right? Now, of course, in that case, the one flying from Accra to Tamale might be the winner because the amount of time that that person will take to fly from Accra to Tamale will be far less than the one that might be getting on the bus or driving or even walking to Tamale. Now, if that is a criteria that is fast time, then the one flying might be the fastest, right? Or might be the most efficient. However, if I say, for instance, the criteria I'm looking at is not time, but cost, how much it will cost to get to Tamale, then maybe the one in the bus might be the cheapest, or the man walking might not have to pay for anything. So that might be the more efficient manner. But what is fundamental for us in this course is that for the same problem, there might be different solutions. You might have a different solution for this problem. I might have a different solution. But at our level, we are not just interested in any solution for a problem. We need to ask further of the solutions for a particular problem, which one is the most efficient? Which is the most efficient of the algorithms for solving a problem? So we need to set a criteria when we say efficiency, which is the best possible solution for this problem. And so we need to learn how to write efficient algorithms. And what we are saying is that if we are able to organize data structures efficiently, and if we are able to write efficient algorithms, then the programs that we write will become more efficient. And that is why the name of this course is called Algorithms and what? Data Structures. It is called that because our main goal is not just to write programs for writing programs' sake. We want to look at making our programs efficient. And the way we make our programs efficient is to use efficient data structures to organize our data and to write efficient algorithms to process that data so that as a consequence, our programs are more efficient. I hope I'm making sense.
Yes,
Yes,
sir.
sir.
Okay. So that is the reason for this course, algorithms and data structures. Now, so that moves us to the question: what are data structures? What are data structures? Now, it says a data structure is a specialized format for organizing and storing data. It is a format that we use to organize and store what? Data. Now, for different problems that we solve, we need to organize our data in specific ways so that it can be worked with. So it says any data structure is designed to organize data to suit a specific purpose so that it can be accessed and worked with in appropriate ways. So for some kind of problem, you might use one type of data structure. For another one, you have to use a different kind of data structure. Our goal is to understand all the different data structures and more importantly, to understand in what scenarios we use these data structures. And there are a lot of data structures that we are going to be looking at this semester. the data structures. Some of them I'm sure you are familiar with. The array data structure. We'll look at the linked list data structure. We'll look at stacks and queues. We'll look at the tree data structure. We'll look at graphs. We'll look at hash tables and a whole host of different ways that data is organized. Our goal is to understand why we organize data in a specific way and what the purpose or for what purposes data is organized that specific way. I hope I'm making sense.
Yes, sir.
All right. So it
Yes.
says data may be organized in different ways. And yes, we organize data in many different ways. But when we organize data, it says a data structure is the logical or mathematical model of a particular organization of data, and it must be rich enough to mirror the actual relationships of the data in the real world. So, what we mean here is when we organize the data, it's not just putting the data in a structure just to put them in a structure, but we put them in the structure to mirror, it says, the real world relationships of the data. What we mean by that is, for instance, if I go into a database of this class, right, and I type your index number, that index number should pull up your name, your date of birth, your course you are doing, your level, your results, and everything that I need. So when we organize data, we are trying to enforce the relationships that exist. So we know that this index number belongs to Kofi Menu, right? And so when I search for this index number, it must pull all necessary information about Kofi Menu that might exist on whatever data store, database, or whatever way we have organized that data. So in the real world, for instance, if you take the alphabets, A is followed by what? B, right? B is followed by C. C is followed by D. If I create a data structure to store the alphabets, it must enforce that relationship. That is, after A, I expect to see what? B, not F. And so if your data structure is not enforcing that real world relationship, then there's something fundamentally wrong with it. We need a data structure or we create data structure so that they mirror the real world relationships that exist in data. So, like I said, we are going to be looking at a lot of different data structures. And for most of these data structures, it says what are they? It says they allow us to represent the inputs and outputs in a way that can be handled efficiently and what? Effectively. So efficiency is our key word here. We use data structures to organize and represent data so that it can be handled efficiently and what? Effectively. And like I said, we'll be looking at the array data structures, the linked list, we'll talk about the tree, queue, stacks, and many other data structures in the course of the semester. I hope I'm making sense.
Yes.
Yes, sir.
All right. Any questions so far? Okay. All right. Then let's continue. Now, when we talk of data and data, organizing data and storing data, there are three ways. If you take any programming language, there are three ways that it allows us to organize and store data. Now, since data can be organized into what we call primitive types, and data can be organized into what we call composite types, and then what is most important to us in this course, since data can be organized using what we call abstract data types. Now, let's look at each one of these briefly. Now, when we say primitive data types, these are basic data types that are built into any programming language. So you've done C++, right? There are a lot of built-in data types that we use there for declaring things like variables and arrays, right? So we all remember the character data type, we remember the integer data type, int, short, long. We also have the floating point numbers as a float, double, and so on. And then we have the Boolean what? Values, bool, right? Now, these all are what we call primitive data types. They are part of the language. They allow us to do very basic data organization. So we can declare a variable, an integer variable that will store one integer value, or we might store create an array of integers that might store multiple integer values. But these primitive types, they are built into the language. They allow us to do basic data management and data storage. But in the real world, data is more complex than that. Data is not just one variable or the other. Take you as a person, for instance. What data can we collect about you? There's a lot of data we can collect, right? Your name, your date of birth, your height, your weight, your blood type, your sex. There's a lot of data that we can collect about you. Now, when it comes to organizing that data, these primitive data types are not enough to organize that data efficiently. And so most programming languages or all programming languages allow us to create what we call composite data types. Composition. It says create your own, compose your own what? Data type. That helps to store data in a more realistic manner. So these composite types essentially allow us to create realistic data types that represent real world data. So, for instance, we have an example here. In C++, if I want to create a composite type, I will use the keyword struct, right? Short for structure. So, I can create a structure in C or C++ that will compose a new data type that can store the kind of data that I want to store. So, for instance, we have an example down here. We are using the struct keyword. So we are saying struct what? Account. We are creating a data type called account. And then we can then define what this data structure will store, the kind of information that it will store. So in the curly braces, we have int account number. So this data type will require the account number of the person, character first name, character what? Last name. So it will require the first and last name of the account holder, and then float what? Balance. So this simple structure here, we are saying will store and organize just these four pieces of information. But in the real world, that is more than enough to know a bit about somebody's account number, their name, and what? The balance that they have on that account. So these composite types allow us to create and manage more realistic data. I hope I'm making sense.
Yes, sir.
Yes, sir.
Okay, all right. But these composite types themselves also lack something fundamental. And what they lack is that they don't allow us, yes, they allow us to create structures that can store data, but they don't go further to allow us to define useful functions that or useful properties or useful functions that this data organization can be used in solving real world problems. Now, we can then solve that problem by creating what we call an abstract data type. Now, abstract data types go further than composite types in one way. That is, they don't just allow us to organize data, but more importantly, they allow us to operate with that data structure in a more efficient manner. Now, when we say an abstract data type, what do we mean? Let me use this example to illustrate. Now, I'm sure you've all heard the word vehicle before, right? We've heard of the word vehicle, right?
Yes, please.
Yes. Now, when we say a vehicle, a saloon car is a vehicle, right? A pickup is a vehicle. A motorbike is a vehicle. A tipper truck is also what? A vehicle. So under this big word vehicle, we have multiple types of what? Vehicle. Now, for different kinds of problems, we use different vehicles. So for instance, if I have a letter in my office and I want to send that letter to someone, let's say in East Legon, right? The University of Ghana. What kind of vehicle would I use to solve that problem? Will I call it a tipper truck? Most likely not. I might call a motorbike dispatch rider and say, take this letter and then ride to University of Ghana, so and so department. ask for Mr. So and so and what? Deliver this letter, right? So I might use that vehicle or I might use a car. I mean, a tipper truck might not be the most efficient vehicle to use. However, if I am building my dream house in East Legon as well, and the foreman calls me and says, "Boss, we are out of sand or we are out of stones, right? And I want to send a trip of sand or a trip of stones to the sites for them to complete my house." A motorbike might not be the best option. Do you agree? A tipper truck would be a better option. Why? Because in one trip, that tipper truck can transport a huge amount of what? Sand and stones. But they are all vehicles. And what are the properties of vehicles? When we say vehicle, vehicles can take people and things from one place to what? The other. But depending on the kind of people and things that we are transporting, we'll use different kinds of what? Vehicles. So if I'm transporting 100 people from one place to the other, a motorbike will not be efficient. A saloon car will not be what? Efficient. The vehicle that will be the most efficient for solving that problem might be a bus, right? That can seat 100 or more people. But they all fall under the same class of objects. They are all vehicles. And so when we create these objects, we create them with the properties that are useful to solve the kind of problems that we are trying to what? Solve. I hope I'm making sense.
Yes, sir.
All right. So when we say an abstract data type, we are talking about creating a data structure or a data type that can be used to solve the kind of problems that are useful for solving the kind of problems that we are trying to what? Solve. So, for instance, we can create a data structure and call it a queue. We all know what a queue is, right? How do we work with queues? How do you join the queue? You join the queue from the back, right? And how do you leave the queue? You leave the queue from what? The front. So we can say, you know what? Let's create a data structure that behaves like a queue. So it will have certain properties. What are those properties? In this data structure, you can only add data at the back of the queue, right? And in this data structure, we can only delete data from where? The front of the queue. And we create such a data structure because for certain problems, we need to organize our data in such a way that the data is following the order of what? A queue. For another problem, we might have to create a data structure that has a different kind of property. Let's call it a stack. So you know what we say? We are stacking cement bags, one on top of what? The other, right? If we stack cement bags, you put one on top of the other. What it means is that you can only access the one at the top. If you go and remove the cement bag at the bottom, what will happen? The whole cement bag stack will fall down, right? Potentially falling down on you. So if I want to get to the bag on the floor, I have to remove all the ones on top of it before I can get access to it. Now, for certain problems, you need to organize your data this way. And so when we create an abstract data type, we create a data type that has properties that we give it that are useful for the kinds of problems that we are trying to solve. I hope I'm making sense.
Yeah.
Yes, sir.
Yes, sir.
Very well, sir.
All right. So in our course this semester, we are going to be creating these abstract data types. We are going to learn how to create data structures that have the properties that we need to solve the kinds of problems that we are trying to solve in the most efficient manner. So we are going to be learning how to create these abstract data types as we go through the semester. So the question is, why do we need data structures? And as I said, the goal of all data structures is to help us what? Organize data. And the reason is to facilitate efficiency. Again, the word efficiency pops up, right? To facilitate efficiency, one, in the storage of data, two, in the retrieval of data, and three, in the manipulation of data. We are not just organizing data to organize it for organizing sake. We want to do so that we are able to store data more efficiently retrieve the data more efficiently, and we're able to manipulate and process the data more efficiently. I hope I'm making sense.
Yes, sir.
Any questions before we move on? Okay. So that is a basic introduction to the concept of data structures to help us organize data. There are different data structures that organize data differently with different unique properties that will be useful for different kinds of problem. Our goal is to know, one, how to create and these data structures, and then two, also to know when to use one data structure over another so that we can be more efficient when it comes to organizing data. Now, as we talk about the different data structures this semester, we'll be hearing about certain fundamental operations that are key to the us understanding how these data structures operate. Now, these operations we are going to be hearing over and over again, and it is important that we know and understand what they are and what they mean. The first of these operations is the operation known as traversing a data structure. Traversing a data structure. Now, when we say we are traversing a data structure, what are we doing? It says we are assessing each record or each data item in the data structure exactly once so that certain items in the data structure or record may be processed. So when we say traverse, we are visiting the data in the data structure. Now, if you cannot access some data in your data structure, it means that there's a problem with your data structure. For different data structures with different organizations, there are specific ways that we assess the values, and it is important that we know how we do that through the process known as what? Traverse. Then another operation that we'll be talking about a lot is searching for data. A lot of what your computer does when it is processing data is looking for the data, searching for that data. There are a lot of different search algorithms out there that we'll be talking about. So it's finding the location of the record with a given value or finding the location of all records which satisfy one or more conditions. We need to learn how to search for data, look at the different search algorithms and evaluate their efficiency as well. Then insertion and deletion, adding data to our data structure and deleting data from what? Our data structure. These are fundamental operations. How can we insert new data efficiently? How can we what? Delete existing data in a more efficient manner. We need to know about these operations with different data structures. Then we talk about sorting. We all know, we've heard sorting, organizing data. When data is sorted, it becomes easier to work with. When data we said is organized, it becomes easier to work with. Sorting data, there are a lot of different sorting algorithms out there. We need to go into learning how we can sort data, how we can organize data, given some specific criteria, arranging that data in some logical order. So we need to talk about sorting. We are going to be learning a lot about how we sort data using different algorithms. And then we talk about merging, combining data from two structures, right? Merging them together into one big data structure. That is another thing that we will be doing this semester. All right. So that is the first part of today's class, looking at an introduction to the concept of what? Data structures. I hope you're all with me. Any questions? But I hope you're all clear.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. All right. If you're all clear, then let's move on to the other part of our course, talking about algorithms. So in the second part of today's lecture, we are going to talk about what we call program efficiency and then talk a bit about complexity analysis of what? algorithms, program efficiency, and complexity analysis of algorithms. Please, NSA Japan, please mute your mic, okay? All right. Now, what is an algorithm? Is the question on our screen. What is an algorithm? Now, there are a lot of different definitions for this concept of an algorithm, or for the word as of algorithm. Let's look at some of them. The first one says an algorithm is a definite procedure for solving a problem in a finite number of steps. Now, what are the key takeaways here? Definite procedure for solving a problem. If it is an algorithm, it must solve a problem, right? If the algorithm doesn't solve a problem, it is not an algorithm. So one key thing is that the problem at the end of the algorithm must be solved. Two, it says in a finite number of what? Steps. Meaning that an algorithm has to begin somewhere and also what? End somewhere. And it follows a process. So step by step, right? So these are the key things that we are taking from this definition. It solves a problem, it has a beginning and an end, and it is a procedure, right? It goes from one state to the other. Now, the second definition here says it's a well-defined computational procedure that takes some values as input and produces some values as what? Output. Again, very similar. From input to output is going from a problem to what? A solution, right? The problem must be solved. And a well-defined computational procedure talks about, again, the well-defined. There's a beginning and what? An end, and it goes through different states to solve that problem. Then we have another one. It says it's a finite number of computational statements that transforms input into what? Output. Again, very similar to the previous two. Now, all of these definitions are correct. All of these definitions are correct. However, for us in this course, we need to add a little bit more to this definition to suit our purposes. Remember, our main purpose is efficiency, right? We want to write efficient algorithms. Now, when we say efficient algorithms, what do we mean? How do we define that? We'll look at that in just a bit. But to say that an algorithm is efficient or more efficient than another, then we are saying that that algorithm is able to solve a particular problem in a more efficient manner, given some criteria. Like we said, going from Accra to Tamale, if it is about cost, maybe being on the bus will be the cheapest. If it is about time, being on the plane will be what? The fastest, right? So when we talk of an algorithm, as I said, for different problems, we can have multiple solutions. But are we interested in just any solution in this course? No. We are interested in only the most efficient, the best possible solutions. And so, because of that, the last definition here speaks more to what we are doing in this course. So, a lot of similar things. It says, one, an algorithm is a finite set of statements, right? That guarantees an optimal solution. So, the solution again is here. It must be solved, it must be finite, and in a finite interval of time. But the part that I want us to focus on is the part that says guarantees what? An optimal solution. Now, what do we mean by that? That is, we are looking not just for any solution, a good enough or a good solution. We are interested in the most optimal, the best possible solution. And so for us, when we are analyzing algorithms, we are not just saying, oh, does it work or does it not work? We are looking at, is it the best possible solution for the problem that we are trying to solve? And if the answer is no, then it means that we cannot say that algorithm is the best possible solution. We need to investigate further to find the best possible solution for that particular algorithm. I hope I'm making sense.
Yes, sir.
Yes, Doc.
Yes, sir.
Okay. So when we break it down. We say an algorithm one is a set of instructions to be followed to solve a problem. And like we said, there can be more than one solution, more than one algorithm to solve a given problem. And it can also be implemented using different languages. But for it to be an algorithm, there are a few things. One, since the algorithm must be what? Correct. If the algorithm is not correct, then it is not an algorithm. It says it should correctly solve the problem. So if I say add 10 to 20, right? And it produces an answer that it says 10 plus 20 is 25, then we cannot call it an algorithm because you and I know that answer is not what? Correct. It must correctly solve the problem. But then we go, it says once we have a correct algorithm for a problem, the next thing that we as information technology students do is we have to determine the efficiency of that algorithm. So we are not just talking about an algorithm being correct. We want to also understand how efficiently or inefficiently it is solving the problem. So if you are looking for who is getting to Tamale the fastest, the person walking to Tamale is solving the problem one way or the other. But is that the most efficient way to get to Tamale? No. The person flying there will be working more efficiently than the person walking because we are interested in how to get to Tamale as quickly as possible, right? And so we are not just saying, oh, it is correct. We are also interested in, is it the most efficient way to go about solving this problem? I hope I'm making sense.
Let's see.
Yes, sir.
All right. Any questions before we move on? All right. Then, if there are no questions, then it leads us to the next question. How do we measure efficiency? How do we say one algorithm is more efficient than the other? How do we come to that conclusion? Now, the way we come to that conclusion is not too difficult, but we need to learn that. So it says computer scientists and information technologies, you and I, we don't just write programs. We don't just write programs. More than that, it says we also analyze the programs that we write. When we write programs, it's not just about writing it, we also need to analyze the programs that we have written. And why are we analyzing? We are analyzing to answer the question, how efficient is this program that you and I have written? And the question that brings up are in fourfold, right? The first question that we are asking is how much time does it take the program to complete? So we're interested in time. If you have written a solution to a problem and I have written a solution to a problem, and your algorithm takes more time than my algorithm to solve the same problem, then we can start to say my algorithm is more efficient than your own. Do you agree?
Yes, dog.
All right. So when we say efficiency, we are asking how much time an algorithm needs to solve a problem. How much time does it take the algorithm to solve the problem? If it takes too much time, we say it is inefficient. If it takes a little time to solve the problem, we say it is more what? Efficient. So that is one part of it. Then the second part is how much memory does the program use? Now, when we run an algorithm on our computer, right, it requires memory to run. It requires memory to run. So for some algorithms, when we execute them, they take up a lot of memory to solve the same problem. Others will use very little memory to solve the same problem. And so we want to know the most efficient algorithms will use less memory to solve a problem. We want to know for each algorithm that we write, how much memory will be required to solve that problem. If that requirement is too large, then we say no, this algorithm is not efficient enough. I hope I'm making sense.
Yes, sir.
Yes, sir.
Yes, sir.
All right. All right. Then the third thing that we want to know is this. It says, how do these changes as the amount of data changes? Now, here, what we are asking is this. It's a very simple question. We expect that if an algorithm, for instance, takes 10 seconds to solve a problem, right? Let's say we have 100 values to add up. Like we said, we are adding all the 100 values in our array so that we can find the total. And then we write an algorithm, and that algorithm takes 10 seconds to solve that problem. What do you think will happen if the number of data it has to process goes from 100 to 1,000? Of course, the expectation will be that the amount of time it will need to process 1,000 will be more than the amount of time it will need to process what? 100. Do you agree?
Very
Yes.
well.
Exactly. Of course. But when we look at algorithms, we start to see something very interesting. For some algorithms, when we move from 100 to 1,000, the amount of time that it will need will rise so quickly, it becomes impractical. It becomes impractical because it needs a lot of time just to process more data. And then for other algorithms, even when the data becomes so much, the amount of time it needs is almost the same or it increases what? Slightly. So we need to understand how, when the amount of data the algorithm is processing is increasing or changing, how does it affect the overall running time and the overall memory use? And once we have this answer to this question, we are well on our way to understanding and analyzing algorithms. I hope I'm making sense.
Yes, sir.
All right. So these three fundamental questions: how much time does it take the program to solve the problem or to complete? How much memory does the program use to solve the problem or complete? And then three, how are the amount of time and the amount of memory use affected when the data that we are processing becomes larger? These are fundamental questions that we ask ourselves as programmers, as information technology students, as computer science students. These are the pertinent questions that we ask ourselves before we can make a determination on the efficiency of an algorithm. Now, the last question there says, what is the difference between the average case and worst case efficiency? We'll talk about that more in just a bit. But I hope you are clear with these three key criteria that we are talking about.
Yes, sir.
All right. Any
Yes, sir.
questions so far? Any questions so far? All right. If there are no questions, then let's take a 5-minute break. And then when we come back, we'll continue talking about efficiency. Okay?
So.
Okay,
All
thank you.
right, sir.
All right. I hope you can all hear me.
Yes, Doc.
Yes, please.
Yes,
Yes,
sir.
Doc.
All right. So let's continue. So before the break, we were talking about efficiency, right? Efficiency of algorithms. And like we're saying, when we talk about efficiency, we want to understand a few things. One, how much time a program will need to complete and solve a problem, right? So one criteria is time. The second criteria is how much memory that program will need to solve the problem. And then the third one is we want to understand how the amount of time and the amount of memory needed will change as the amount of data it is processing also change. We said for some algorithms, the amount of time and memory needed will increase quickly. For others, it will increase slowly. We want to know that. So let's move on and understand. So when we say efficiency, efficient algorithms, what do we say? One, we say the program takes less what? Memory to solve a problem, what we refer to as being space efficient, right? So the programs that need less amounts of memory to solve the same problem. So given the same problem, one program might need less memory than the other. The one that needs less memory, we say, is more efficient than the one that needs more memory. Then the amount of time, execution time, the one that needs smaller amounts of time to execute and solve the problem, we say is more efficient than the others. Now, we can also look at things like the programming time as a criteria, but it doesn't really tell us too much. And what is most important to us is something known as the time complexity. Time complexity. And we'll talk about time complexity in just a bit. So when we talk of efficiency, we are talking about the amount of time and memory needed, and also how the amount of time and memory needed to solve a problem increases as the amount of data we are working with increases. So to sum it all up, like I said, when we write programs, we don't just write programs as information technology students. We also analyze. We need to analyze the algorithms or the programs that we write. And the question is why? As we said, we're analyzing for two things. The first one is correctness, right? We want to ensure that the algorithm that we have written is doing what it is supposed to do. So if it is to add numbers, it is actually adding numbers and not subtracting or multiplying. We want to make sure the algorithm is correct. That is why we analyze. But secondly, the most important reason why we analyze, as we said, is to understand the performance of that algorithm and the performance in relation to the running time, how much time it takes for the algorithm to execute or run and solve a problem. And then two, how much storage or memory is needed, again, to solve a particular problem. And so we are interested in how much time and how much memory these algorithms need. So to define an efficient algorithm, we are talking about an algorithm that consumes a lesser amount of resources while solving a problem of size n. And we'll talk about what size n means in just a bit. So the algorithm that consumes the lesser amount of what? Resources while solving a problem of size n. And what are these resources? Memory and what? Time is said to be the most efficient algorithm. Now we say a problem of size n because for us to be able to evaluate efficiency, they must all be solving the same problem. So what we mean by that is if algorithm A is processing 100 values, algorithm B must also be processing the same 100 what? Values for us to be able to compare. Now, if one is solving 100 values and the other is solving 10,000 values, we cannot compare. They are doing different things. Whatever the running time or memory usage in different for the two problems cannot be compared. So to be able to compare them, we say they are solving a problem of what? Size n, right? That is a problem that is of a fixed size, and it is the same type of problem for all of the different algorithms. Once we have this scenario in place where they are all solving the same problem, then we can make a determination and say algorithm A is more efficient than the other. Why? Because it uses less time to solve the same problem, and it uses less memory to solve the same problem. I hope I'm making sense.
Yes, sir.
Sure.
Okay. So that leads us to the next question. How do we measure efficiency? How do we say Dr. Brown's algorithm is more efficient than Kufumianu's algorithm? How do we come to that conclusion? Now, the most obvious answer might be, so do we just measure the processor time and say one is better than the other? Let's find out if that is the case. Now, when it comes to measuring efficiency, we need to understand this, that the efficiency of an algorithm, as we are saying, is a measure of the amount of resources consumed in solving a problem of size n, right? So how much time will an algorithm need to process a problem of size n, and how much memory will the same algorithm need to solve a problem of size n? Now, for today, the resource we are going to focus on is time, right? This is the most important resource we are most interested in today. It's the amount of time. So we want to know the amount of time consumed to solve a problem of size n. And it says we can use the same techniques to analyze the consumption of memory as well. But today, we are going to focus on the amount of time needed. Now, when we do the analysis for an algorithm and we measure the efficiency, when we measure the time, how long the program runs, we are measuring what we call the time complexity. And this is important, so write it down somewhere. When we measure the amount of time or how long a program runs to solve a problem, we are measuring what we call what? The time complexity. And then when we measure how much memory it uses, we are measuring what we call what? The space complexity. So our job today is to learn how to measure the time complexity of an algorithm. Measure the time complexity of an algorithm. And this brings us back to the question we asked a bit earlier. It says it will seem that the most obvious way to measure the efficiency, the time efficiency of an algorithm is to run that algorithm on your computer and measure how much processor time it took, right, or is needed. So we put our algorithm into a compiler, we click execute, it executes, it gives us the solution, and then we measure how many seconds or minutes did it take to what? Solve this problem. Now, is this right? Is this correct? Is this the way forward? The answer, unfortunately, is what? No. And the reason for that is if we run an algorithm on our computer and we measure the amount of time it takes, there are a lot of variables that will influence that time. Now, what are some of these variables? It says the same algorithms running on different processors don't take the same time. Why? The processor speeds will be different, right? So on your computer, your processor speed goes up and down. And so even if your algorithm is bad, it's not the most efficient. If the processor speed is fast enough, it will look very efficient, right? And so a less efficient algorithm will look more efficient than the more efficient algorithm because the processor speed is influencing it. Apart from time, the type of processor will influence it. The programming language used will influence the running time. The quality of the compiler will influence the running time. Even the operating system that we are running the program on will all influence the running time. And because we cannot control these variables, we need to do something else. We need to find a way where all of these variables will not influence the running time, right? So the best way I can explain it is we say we want to find the fastest person in this classroom. And then the way we do it is that some of us are running on track, some of us are running inside the pool, right? Now, of course, if we are all running on track and I finish before you, I can say I'm faster than you, right? But if I'm running in the pool and you are running on land, then there are factors that are impeding my speed, right? Running in water can be difficult. And so in that scenario, if we finish, can the person who is running on land actually say that I am faster than the one inside the pool? No, because you are doing two different things. We want to measure the efficiency in such a way that we have a level playing field. I hope I'm making sense.
Yes, sir.
Yes, sir. Yes, dog.
Okay. Yeah.
Yes, sir.
So in measuring the efficiency, we want to measure it when all of these variables that we have here are eliminated. They don't influence the running time. And so the best way to measure the efficiency is to do something we call a theoretical what? Analysis. Instead of executing the code on the computer and testing the amount of time, we simply do a theoretical analysis. Now, what happens, or what is a theoretical analysis? What happens during the theoretical analysis? Now, during the theoretical analysis, we eliminate all the hardware and software factors that can influence the running time. So we want to eliminate processor time and speed and compiler type and operating system. So instead of putting your code on the computer to run, it says we use a high level description of an algorithm instead of an implementation. So we are going to analyze the code in its written form. We're not going to run it at all. We are going to analyze the code on paper, right? We are going to write the code and analyze it on paper. And the reason for that is that when we analyze on paper, the compiler type will not influence it. The processor type and processor speed will not influence it. The operating system will not influence it. We eliminate all of these variables from the equation, and the only thing that remains will be one, the fact that they are all solving the same problem. So the input size will be the same for everyone, and they are all doing that in an environment that is free of any influence that potentially can skewer the results in one way or the other. I hope I'm making sense.
Very well, sir.
Yes, dog.
So, so it says that it characterizes the running time as a function of the input size. And what this means is that we measure the running time based on the input size, right? So, for instance, let's say we've given an array of 100 values to an algorithm. We want to understand how much time will it take it to process that 100 algorithms. And when we say time, what are we talking about? The time we are talking about is basically the number of steps it will need to solve that problem. The number of what steps it will need to solve or add up all those 100 values. Now, when we do a theoretical analysis, the only thing that will be different will be the number of steps, because the nature of and number of the inputs are the same. They are all solving a problem on what size n, right? They are all solving. So if it is a million integer values to add up, they are all adding up a million what integer values. The only thing that will be different will be that for one algorithm, it will need 2 million steps to process that million integer values. For another algorithm, it will need 10 million what? Steps to process that 1 million integer values. And once we know and we can count the number of steps an algorithm will need, we can then say, well, this algorithm needed more steps or more operations than the other one to process the data. I hope I'm making sense.
Yes, please.
Okay. So it says that running time will be measured in terms of the number of steps / primitive operations that an algorithm performs. So given an input size, given n, given some data, how many steps do you need to process the data? And how many steps does another algorithm need to process that data? Once we have that information, we can compare and contrast and say one algorithm uses less steps than the other to solve the problem. And when we do this, as we said, all the hardware, software, processor type, speed, or compiler, operating systems don't play any role here. The analysis is purely theoretical. It is not practical. I hope I'm making sense.
Yes, sir.
Yes, sir.
Okay. So when we say we are analyzing an algorithm, when we are going to analyze an algorithm, it says we are finding the running time of that algorithm. And what does that mean? It says the running time is measured by the number of what? Steps or primitive operations performed. The running time is measured by the number of steps or primitive operations that are to be performed. And when we say steps or primitive operations, what are we talking about? We should know them: addition, multiplication, less than, assignment, subscript, any operation. So, for instance, if your algorithm has 10 addition operations, then it means that we have to count all 10 addition what? Operations. If your algorithm has 100 assignment operations, it means we have to count what? All the 100 assignment operations. So by counting these operations that are performed in this algorithm, we then have a fair idea. So this algorithm will perform 1,000 assignment operations and 500 addition and 200 multiplication and 500 less than and greater than operations. And as we count, we start to get a picture of the overall amount of operations that are going to be needed to solve that problem. I hope I'm making sense.
Yes, sir.
Yes, sir.
Okay. All right. So to be able to analyze an algorithm, there are a few assumptions or a few things that we need. One, since we assume that the input size is n, right? And when we say input size is n, we are saying the input size is the same for all algorithms. And then when we say primitive steps, we are talking about the operators that we all know. But before we analyze two, we need to be careful. So for instance, if we are analyzing an algorithm that has a loop, right? We all know loops: for loop, while loop, do while loop. If there's a loop in that algorithm, we need to know that because there's a loop, certain operations will not be counted once. So if the loop will execute 1,000 times, it means that one addition has to be counted what? 1,000 times because it is inside what? A loop. We need to be cognizant of the control structures, and we need to understand when we, for instance, have a loop or an if-else statement, and know how to count those operations as well. So let's try one. Let's analyze a piece of code here and see how the analysis itself will be done, right? So we have a very small function here. It's a function that is called sum, S-U-M, right? And this function is going to, the input into this function will be an array of n values. So it's an array of what? N integers. We are saying n, we don't know the number of integers yet. So we are using the generic term what? N. Now, what is this function supposed to do? It says the output of this function will be to sum up all the numbers in the array A, right? So it's going to take all the numbers in this array, all the integer numbers, and find the total, the sum of all of these numbers. And so that is our piece of code here that we are going to analyze for running time. Now, how are we going to go about it? The first thing that we need to do is to identify all the operations. So all the operations have been highlighted now, right? There are 8 operations that have been highlighted. So the first operation here is an assignment operation. So it says S is assigned 0. The second operation is another assignment operation. I is assigned what? 0. The third is a less than operation. I is less than n. The fourth is an increment operation, right? I plus plus, meaning that I will increase by 1. Then we have number 5, which is another assignment operation. Number 6 is an addition operation. Number 7 is a subscript operation. So the brackets there are an operator. They are a subscript operator. And then the last operation is a return operation here. So we've identified what? 8 different what? Operations. I hope you're all with me so far.
Yes, sir.
Yes, we are following.
Okay. So we began the analysis. We first identified all the different operations. But before we count, let's take note that there's a loop here, right? We have a for loop here. So like we said earlier, when you have a loop, certain operations you can count once, but if there's a loop, it means that certain operations have to be counted multiple times. So we have to count it, the number of times the loop will execute. So let's do this exercise. We are going to take each operation one by one and determine whether we'll count it once or count it multiple times. In this case, n times. We are saying I should be less than what? N, right? So we want to count. Certain operations will be counted n times. We don't know the value of n yet. Later we'll do an experiment with different values of n. So we want to see which operations will be executed once and which operations will be executed n times because they are part of the loop. Now let's take a look at operation 1. Operation 1 is outside our loop. It is not part of our loop. So it means operation 1 will be executed only what? Once, right? Then operation 2, I is assigned 0. Now, this is inside the loop, but it is what we call the initialization of the loop, right? The initial state or initial statement. The initialization is only done once. So operation 2 also will be executed what? Once. I hope you are following so far.
Yes, sir. Can you come again?
Yes, sir.
The assignment.
So operation 1 and operation 2, they are not part of the loop. Operation 1 is outside the loop. It will be executed once. Operation 2, even though it's inside the bracket of the loop, it is not part of the loop. It is the initial state. It's the starting point of the loop, right? We're only going to start once. So operation 2 will also be counted once. So 1 and 2 will be executed once. Now let's look at operation 3. Operation 3 is the condition of this loop. The condition says that I must be less than what? N. Now this condition is what is going to control this loop. So this condition here will execute n times. So it means that operation 3, being the condition for this loop, will execute n times. The same for operation 4, the increment, right? So I is starting from 0. We are going to increase I n times till we get to what? N, right? So it means that this increment operation will also execute what? N times. So 3 and 4 are part of the loop. They will execute n times. Now operations 5, 6, and 7. This entire statement is linked to our loop. So it means that operation 5, this assignment operation here, operation 6, this addition, and operation 7, the bracket or the subscript operation here, are also all going to execute how many times? N times. And then the last operation, operation 8, it is not part of the loop, so operation 8 will execute only once. So in total, this is what we are going to get. Operation 1, operation 2, and operation 8 will execute how many times? Once, right? And then operation 3, 4, 5, 6, and 7, it says they will execute once per each iteration of the loop. How many iterations are we going to have? N iterations, right? So it means that these 5 operations will execute N times. I hope you're following so far.
Yes, sir.
Yes, sir.
Okay. So of the 8 operations that we've identified, these 3, 1, 2, and 8 will execute once. And then these 5, 3, 4, 5, 6, and 7 will execute N times because they are all linked to the loop. So we can say the total number of operations will be these 5 operations here. How many times? N times. So 5 times what? N. So these 5 operations, N times, plus these 3 operations that are going to execute what? Once. So 5N plus 3 here is representing these 5 operations, that is operations 3, 4, 5, and 6, executing what? N times. So 5 times what? N, plus these 3 operations, that is 1, 2, and 8 up here. So the total number of operations for this algorithm we are going to say is 5N plus what? 3. Am I making sense?
Yes, sir.
Okay. So the 5N plus 3 here, that is 5 operations N times plus 3 other operations, will be the total number of operations that are going to be performed on this algorithm. Now, mind you, we don't know the value of N yet, right? So that is why we are writing this expression. And this expression, the 5N plus 3, is what we call the complexity function for this algorithm. So the complexity function for our algorithm here is 5N plus 3. That is basically saying that for this algorithm, of the 8 operations we identify, 5 of them will execute N times, and 3 of them will execute what? Once. That is why we have 5N plus 3. I hope I'm making sense.
Sir, please, I have a question.
Go ahead.
Please, with this concept, is it giving us this concept in C? As in, you can use the same concept in C and to get the same answers with this. Will it be okay?
When you say giving it in C, I don't get. You mean the language C?
Yes, yes.
It doesn't. So it doesn't really matter the language you're using. Again, what is fundamental is that whether it is C, C++, Java, what are we counting? We are counting the number of what? Operations. Are you following?
Yes, please.
So any time an operation is performed, we have to count it. So that's why we're saying for this algorithm, we have 8 operations that we are counting. But because some of the operations are inside the loop, 5 of them, we are saying those 5 operations will be executed what? N times, right? 5 times N, right? And then these 3 operations will be executed once. So if we wrote this code in C or Java or any other language, I mean, yeah, maybe 1 or 2 operations might be different, but once it's an operation, it has to be counted. I hope I'm making sense.
Yes, please. Thank you.
All right. Any other question? All right.
Hello,
So, yes, go ahead.
Doc. So apart from the manual counting, we don't have any button on the IDE to do this counting.
And that's what we said exactly. When we analyze, we are doing a theoretical what? Analysis. If you bring in an IDE, you're going to execute. It will influence the results. So, as we said, we do a theoretical what? Analysis. I hope I'm making sense.
Yeah, Doc.
Okay. All right. So, the 5N plus 3 here is telling us some information about this algorithm. That there are 8 identified operations. 5 of them will be executed n times. 3 of them will be executed what? Once. And so the total number of operations will be 5n plus 3. And remember, if you remember, we said the running time is a function of the input size, right? So the input size n here is going to help us determine the total number of operations. And we'll look at that in just a bit. But this 5n plus 3, what we write as f of n is equal to 5n plus 3, is what we refer to as the complexity function. Now, let's do an experiment. Let's estimate the running time for different values, right? So, for instance, if n is equal to 10, right? If the array has 10 values, then we are saying that approximately that algorithm will need how many steps? 5 times 10 plus 3, it will need what? 53 steps, right? If n is 100, then 5 times 100 plus 3, it will need what? 503 steps. If n is 1,000, we are saying it will need what? 5,003. If n is 1,000,000, it will need what? 5,000,000 and what? 3 steps. So, given different values of n, we can roughly estimate the number of steps that algorithm will need to process those values. So, if n is any of these values, it's just substituting the value of n into that expression that we saw earlier, 5n plus 3, and calculating the number of steps that will be required. I hope you are following.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. All right. So when we get our complexity function, we can then estimate, given
Hello, sir.
let me finish, you can come in a bit later. So when we get our complexity function, then as we said, we can estimate, right? The number of steps. Again, the key word here is what? Estimate the number of steps that an algorithm will require to solve a problem given a particular input size. All right, somebody had a question, go ahead.
Yes, sir. Please go back to the code.
Yes.
Okay, so from my side, I normally see return as 0. But from this code, the return is S. So I would like to know the differences.
My brother, if you don't know the difference, then you shouldn't be in this class, sir. If you don't know the difference between return 0 and return S, then you shouldn't be in this class. You remember the last time I told you to go and get refresh on your C++, right? Do you remember? Hello?
Yes, please.
Yes, sir. Yes, sir.
Yes, and if you don't know the difference between return S and return 0, we are in trouble. If you don't know the difference between return 0 and return S, it's like SSS student asking you, say, what is the difference between 1 plus 1 and 1 minus 1? These are fundamental things that you should know. You have gone through 2 courses on programming. Introduction to Structured Programming and programming with what? C++. Did you do functions under C++? It's a question. Did you do functions in C++?
Yes, sir.
Yes, sir.
And in functions, do you return values back to the main program?
Yes, sir.
And how do you return those values? You have what? A return statement. Return what? Some value, right?
Yes, sir.
And then what is the difference between that? When we see a return 0, what does that mean?
So it means the program runs successfully.
Exactly. So please, if you don't know these things, I know you think you're asking a smart question, but you're exposing yourself. Go and learn C++. Trust me, the course is entirely based on C++. If you don't know C++, it will be a very long semester. I don't want you to suffer. So please make a choice now. Go and revise. Go on YouTube. Go and look for tutorials on C++ in what? YouTube and start watching. Start building your skill. I know some of you barely pass your programming with C++ course and are now here, but I cannot go back to go and teach you C++ and then continue with my teaching. I'm going to teach as if you know C++. So if that is not the case, I beg you and I beg you again, go and do something about it. I hope I'm making sense, everyone.
Yes, sir.
Yes, please.
Yes,
Yes.
sir.
Look yourself in the mirror and ask yourself, do I know C++? If the answer is no, I beg you again, go and change the answer to yes. Because if the answer remains no, the semester will look like Kakai. You know what Kakai is, right? So
Okay.
please go and learn. Go. Luckily, you live in 2026. The fact that you are all logged into this class means you all have computing devices, either laptops or mobile phones. Excellent. Stop watching YouTube videos on songs and non-fa. Use your data to watch C++ tutorials. Go on websites that will teach you C++. You should know a language by now by heart. You should be excellent in at least one programming language. C++ is a good place to start. If that is not the case, please do something about it before it is too late. As for the excuses, they'll say the teacher, I don't care. Go and learn C++. I hope I'm making sense.
Yes, sir.
Yes, sir.
Okay. All right. So was it Lukman who was asking that question? Lukman, next week I will ask you this question again. If you don't know the answer, me and you will have a fight all semester. I hope I'm making sense. Hello, Lukman, are you still with us? I've scared Lukman away. Don't worry. But that is all, that message is to all of us. Go and build your C++ skill. All right, let's get back to where we are. Time is gone, right? We should be finishing up. So we have calculated that for this algorithm here, when we analyze it, we identified 8 operations. 3 of them were executed once. 5 of them were executed n times because the array is processing n values, right? And to iterate n times. So we said the total number of operations is 5n plus 3. And then when we did the estimation, we are saying that if the array had 10 values, this algorithm will need 53 steps. If it had 100, it will need 503. If it had 1,000, it will need 5,003. If it had 1,000,000, it will need what? 5,000,003. Now, what do we see here? What trend do we see here? And it is this trend that is very, very important. Now, let's see here. As n is increasing, so we'll go from 10 to 100 to 1,000 to what? 1,000,000, right? What do we see happening to the number of steps? As n is increasing, we also see that the number of steps is what? Increasing.
Increasing.
Do you agree?
Yes, sir.
Yes. And if you remember, when we're talking about efficiency, we asked the question, what happens to our algorithm when n is increasing? How does that affect the number of operations? And here we see an interesting trend, or not a very common trend. As n is increasing, the number of steps are also what? Increasing. And if we pay attention, we notice that there are increasing in linear proportion, right? There's a linear proportional increase between n and the number of steps. As n increases, as n grows, the number of steps also grow in what? Linear proportion to n for this function that we just analyzed. Now, this linear proportional growth that is happening is what we are really looking for. This linear proportional growth that is happening is what we are most interested in. In fact, when we analyze algorithms as information technologists, computer scientists, we are not really interested in the exact number of steps. So whether it is 53 steps or 5,000,003 steps, it's not really of concern to us. It's not really what we are interested in. What we are really interested in is how this algorithm behaves in relation to the input size, how the number of steps grows in relation to the input size. And as we do this simple experiment here, we see that trend popping up, right? As n is increasing, there's a linear proportional growth between the input size and the number of steps. And this relationship gives us a very important clue about the algorithm that we just analyzed. And what is that clue? That clue is that this relationship is going to continue even as n becomes larger and what? Larger. As n moves from 1,000,000 to 1,000,000,000 and 1,000,000,000, we expect that the number of steps will also grow in the same what? Pattern, in linear proportion. I hope I'm making sense.
Yes, Dad.
All right. Now, it is this pattern that we are interested in. Why are we interested in this pattern and not knowing the exact number of steps? The reason is very simple. Now, if I take 1,000,000 values and I give it to a computer, it will process it in a few seconds, right? You won't see any difference between algorithms. Even a bad algorithm processing 1,000,000 values will do it in a few what? Seconds. The same, an excellent algorithm processing 1,000,000 values will also what? Process it in a few seconds. Now, when it comes to understanding the efficiency of an algorithm, we are able to see the differences between algorithms when this n, when the input size is moving towards infinity. We've heard the word infinity before, right?
Yes, sir.
Let's go.
When n is moving towards infinity, when n is becoming extremely large, what we call the worst case scenario. Now, the worst case scenario is when we are dealing with extremely large values of n. In the worst case scenario, as n, the input size starts to trend towards infinity, what is important to us is not how many exact steps the algorithm will perform, but what is important to us is that the number of operations will be growing in proportion, in linear proportion to what? N. The number of steps will grow in what? Linear proportion to n. And that is the most important thing that we are interested in when we analyze an algorithm. We are saying this algorithm, when the data it has to process becomes extremely large, how will it behave? And this experiment here is telling us how it will behave. It is telling us it will grow in what? Linear proportion. And that is what we analyze for. So we are not analyzing to know whether it will do 5,003 steps or 5,000,003 steps. No. We are analyzing to understand how this algorithm will behave as n trends towards what? Infinity. And we know that as n is moving towards infinity, the number of steps it will need will be growing in linear proportion. So it will also be trending towards what? Infinity. And once we have this pattern, it is enough for us to conclude on how this algorithm will behave in the worst case scenario. So when we analyze algorithms, we are trying to see what will happen to this algorithm in the worst case scenario. And as we can see here, in the worst case scenario, this algorithm will grow in linear proportion to n for the algorithm that we just analyzed. I hope I'm making sense.
Yes, sir.
Yes, sir.
Okay. So when we analyze an algorithm, we are not really interested in whether it will perform a million or a billion operations. No. We are really interested in how or what happens to that algorithm as the input size becomes extremely large and starts moving towards infinity. And here we see with our 5n plus 3, as n gets large, it says the plus 3 becomes less and less what? Significant. The plus 3 becomes what? Insignificant, right? So we can drop the plus 3. It doesn't really tell us anything. And as n also gets large, the 5 also becomes inaccurate. The 5 times n here, we are saying that these 5 operations will execute n times. But we are also making assumptions that all of these operations will run in the same amount of time. But it doesn't really matter. What matters most is that when n, the input size, is moving towards infinity, the number of operations, let's call it O, will be growing in linear proportion to n, right? And it will also be moving towards infinity. So we are saying here that 5n plus 3 will grow in linear proportion to n. It says what is fundamental? What is fundamental is that the time is linear in n. The number of operations, the amount of time this algorithm will need to solve a problem will grow in linear proportion to n. It will also be trending towards infinity. When we do this, we are saying we have described what we call the asymptotic complexity. The asymptotic complexity. The asymptotic complexity basically says as n gets large, as n moves towards infinity, it says we need to concentrate on the highest order term. The highest order term is n. So as the input size n moves towards infinity, the number of operations will also grow like n. That is, it will also trend towards infinity. And it is that pattern, it is that behavior that we are interested in most because it gives us a good idea about how this algorithm will behave in the worst case scenario. And it is that relationship that we are going to use to describe different algorithms and their behaviors as n moves towards infinity. So for every algorithm that we analyze this semester, we are going to be analyzing it under the scenario that n is moving towards what? Infinity. We are not dealing with small values of input. We are dealing with extremely large values of input. And it is when we are dealing with extremely large values of input that we can really begin to tell the difference between algorithms. Because if you give any algorithm a small amount of input, they are all efficient enough. We are able to make the distinction between different algorithms when it is in a worst case scenario, when n is so large that it is moving towards infinity. And in this example that we just saw, we see that when that happens, the number of operations will grow in linear what? Proportion. And that is all that we need to know to understand about what this algorithm will behave like in real practice. I hope I'm making sense.
Yes, sir.
All right. So with our asymptotic complexity, we say that the 5n plus 3 time bound is set to grow asymptotically like what? N. It's set to grow asymptotically like what? N. What this means is that the input size, as it goes towards infinity, the time bound, the amount of time this algorithm will need, would also grow just like N. It would also be growing, leading towards what? Infinity. It will grow in linear proportion. And it says this gives us an approximation of the complexity. And this is very important. We are interested in what? Approximating, not exact figures. We are interested in an approximate behavior of the algorithm. So we are not here to count whether this algorithm will do 1 million operations or 1 trillion operations. If I said count 1 trillion operations, you will be counted till you're 60 years old, right? No, we are not here to count. We are here to approximate. Sorry, there's a lot of noise here. All right, sorry about that. So we are interested in what? Approximating, approximately, how this algorithm will behave. And what we can conclude is that as n is moving towards infinity, the number of operations will do the same. It will also be moving towards infinity. They will be growing in linear proportion. I hope I'm making sense.
Yes, sir.
Okay. All right. Any questions for me before we move on? All right. If there are no questions, then write down your homework for next week. Are you ready?
Yes, sir.
All right. So your homework for next week is simply this. You're going to go and write an essay about time complexity. You're going to write an essay about time complexity and what we call the big O notation. You're going to write an essay about time complexity and the big O notation. Writing an essay about time complexity and the big O notation. Now, when you do this essay, when you're writing and researching about this essay, especially about the big O notation, the big O notation will show you the different categories under which we place algorithms, right? The big O notation will give you the different categories under which we place algorithms. For each category, so for instance, we have the first category is constant time, then we have linear time, quadratic time, and so on. So for each category, you are supposed to find 3 examples. For each category, you're supposed to find what? 3 examples of algorithms that fall under that category. For each category, you're supposed to find 3 examples that fall under that category. I hope I'm making sense.
Yes, but why don't you put it on the LMX?
My brother, let me finish giving this. I've not told you where to put it. I said, go and write what? an essay.
Okay.
So when I finish, then I'll tell you how
Okay.
to submit it.
Okay. Thank you.
So you write the essay, and then Friday by 5 p.m., there'll be a link on the learning management system. You're supposed to submit your essay, typed up essay, onto the LMS by 5 p.m. on Friday. I hope I'm making sense.
Yes, sir.
Yes, sir.
Yes, sir.
Now, mind you, I said go and research. I didn't say go and use ChatGPT. I said go and what? Research.
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 It means you have to go and read and do the work, not go and dump the question in ChatGPT and see what it spits out. Because randomly next week, I might pick one or two of you to explain one or two categories. I'll just choose a random name and then that person will be required to explain. It could be anyone. I will just go through the list of names and select you. And if you're not able to do it, I'll give you a 0. I hope I'm making sense.
Yes, sir.
Yes,
All right.
sir.
Okay, so that will be your homework for the upcoming week. I'll meet you guys next week online again. All right?
All right.
Okay. So bye-bye. I'll see you guys next week.
Okay,
Yes,
bye.
sir. Thank you.
Thank you.
Thank you.
Allahu Akbar.